Okay, so let's summarize what we have discussed so far. Although last time we were mainly did the computation by Go programming language. So far we discussed the double integral of two variable function on a certain domain. Okay, so we discussed that we can compute this double integral using Fubini theorem by iterated integral, and also we discussed a triple integral of three variable function, and there was a generalization of Fubini theorem to compute the triple integral using triply iterated integrals. So what we are trying to do from now on is to introduce some techniques of integration, and that is integration by substitution. Although I said this is a technique, but it contains a main idea of what is the differential of a function, and more specifically, what does the differential of transformation means. And also, when you understand the meaning of differentials, then we can discuss about the line integral and surface integral and integration of vector field and so on, which will be the next topic after we discuss this. Okay, so that's our summary. I left this right-hand side blank because I want to fill out something, because so our goal is to compute this double or triple integral, and the way we can do this is by taking iterated integral if the domain or volume is given in a nice way. But even if the domain is given in a nice way, if you have a formula which is very complicated to compute your integral, you have to change your variables, or more specifically, you have to substitute your variable to new variable to make your computation easier. So that's the idea of substitution, integration by substitution of single variable function, right? So let's rewrite the integration by substitution for single variable function case. It means that, let's say, all right, well, there's an all right, well, let's say t dt. How do you write this? So maybe let me give an example here. So if you want to integrate from 0 to 1 of 1 plus t squared dt, what do you do? Substitute t with sine, right? Let's say sine theta, and you take the exponential increment of t, then it's approximately infinitesimal increment of theta, but we have a coefficient cosine d theta, so we'll substitute t by sine theta, and dt by cosine theta d theta, right? And when you do that, you have 1 plus, well, does it make sense? Let's make it minus, make it easier, okay? So 1 minus sine square is cosine square, but you have a square root of cosine square, So it could be a negative, a plus minus, but we're taking a t from 0 to 1. So basically, we're taking the range of theta to be 0 to pi over 2. And we know that cosine theta is always positive in this interval. So we can safely say that this is just cosine theta. And then d theta is cosine theta, d theta. And the problem is you have to change the limits of integration variable. So when t is 0, you take theta to be 0. And you take t, to make t equals to 1, you take pi over 2. So you have to, you now change the integration, which is something that you can actually compute by your hand. So let's think about what's going on in doing this, okay? So we had practiced this integration by substitution as if it's just a technique of integration. But we have to understand why we can do this, right? So think about the function defined on the interval 0 to 1, this function in terms of t. So if I draw that function t, let's say y, for example, then it starts from 1, and then it ends at 0. And is it concave up or down? How does it look like? Does it look like this, or does it look like that? Yeah. So it looks like this, right? So this is a graph of function. So instead of taking t as our domain, what we were trying to do is try to make theta as the parameter of function determining its value. So I'm going to take a map, which is the axis of theta instead of t, and I want to parameterize t in terms of theta. So I should take a map which sends the unique value of theta to a unique value of t. So that's our sine theta. Can you see this part? Okay, so that's a sine theta. So this is sine graph. So when theta from 0 to pi over 2, t range from 0 to 1. And you know that this is one-to-one function. Only one value of theta in this domain from 0 to pi over 2 maps one value of t here. Okay? So you can identify your t, one value of t, by taking one value of theta. And so when we integrate this thing, what we are actually doing is taking a small area of inside or almost equal size of this underlying graph, and then we take the height here, and then we take the width here, right? And then multiply together and add all up, and by sending to the limit, we get the actual area under this function. But if you change your parameter to theta, the d theta, the increment of theta, is not in the same ratio of increment of t, right? So if you change your theta at some point, a small amount, then your value of t also increases, but it depends on where you take the increment and also it's not 1. It's not always 1. So how to measure the ratio between the increment of theta and the respective increment of t, you should take the differentiation. So t is a function of theta. So if you take t prime theta, this is basically delta t and delta theta, basically, right? And this is equals to cosine theta, right? So that's how we get the dt equals to cosine theta d theta, right? So when we do the integration by substitution, we're not just technically replace these symbols to this symbol. What we're actually doing is try to compute the area under the function, but in a different setup, different parameter. Say we have a width of these small rectangles. Height is okay, but width depends on, width, the delta theta is not same as delta t is not equal to delta theta. I want to express delta theta in terms of delta t in terms of delta theta. So I have to correct that by the ratio between delta t and delta theta. And then, of course, the height was in terms of t, but now I have to change it to in terms of theta. Then I have to replace my t in terms of theta. Then this whole thing also changes in terms of the function in terms of theta. So that's what's going on here, right? So let's look at the multivariable function case. And I'm going to draw a picture of a graph of two-variable function in this way. So we have a domain of two-variable function. And let's say this function is real-valued function. Okay. So if you want to graph this, graph the graph of function, then it will be like this surface in the three-dimensional space. Okay? So this surface is the graph of function. But what happens if I split the domain and the range, then the function is sending two-dimensional point on two-dimensional plane to a single real value, right? So that's a two-variable function. Now, let's say I have domain here. For now, let's take D as a rectangular domain. For some reason, let's assume that for some reason, taking a double integral on this rectangular domain of this two-variable function f is hard. So I want to change my variable x and y with different symbols. Okay, so different formulas. Let's say u and v. Okay. Now what I have to do is I'm doing the same thing as we defined in the double integral. I'm trying to take the double integral, which is symbolically written as this, and then its meaning is the volume under the function. Okay, so I'm trying to take a small area or a small subdivision of this domain D, and then take the rectangular cube and find the volume of small rectangular cube, and then add all up and take the limit and find the volume, right? So I'm doing this, but to do that, I have to specify the point I'm taking inside of this small rectangular domain. So if I take the point here, I can find the height of this rectangular cube, okay? And the width and the area of this small rectangular cube is delta x times delta y, right? So the problem is I have to know which point in UV plane maps to x star and y star, and I also have to know how to express this delta x delta y in terms of delta u and delta v, because I'm trying to replace everything in terms of x and y in terms of u and v. Okay. So I'm going to introduce another function called t. So t stands for transformation. Let's say my transformation maps let's say in this case E here. So it's another name for domain. And so this transformation is one-to-one, which means that I have injective mapping, which means if I take a one point in this domain D, then this point is the point in the range of transformation, which is the simple function from two-dimensional planes to two-dimensional plane. There is only one point in the domain that maps to this unique point. That's the one-to-one map. And then it's surjective. That means if I take any point in the domain D, which is the range of T, then I can always take at least one point inside of domain E of transformation T that maps to this point. Let me write that. As a definition, a transformation in general, it doesn't have to be two-dimensional plane to two-dimensional plane. It can be just Rn to Rn function. Is a map, is a one-to-one surjective map. I want to say in a Korean word because it will make it easier. So one-to-one is 반사함수, and surjective means 전사함수. Okay. So in other words, you can call it a injective and surjective map, and there's a word for saying if both map is both surjective and injective, it's called bijective. All right. So I have transformation, and what I need to know for now, I can find out a unique point in the domain E to corresponds to the unique point in D using the transformation T, and taking the height in terms of UV is no longer a problem. Okay. But now I have to change my delta x, delta y in terms of delta u and delta v, because if I take a small increment of u in the UV plane and v here, right, I get a small rectangular box, and that small rectangular box is not going to be the same area with the delta x, delta y. So I have to replace that. So I need to find out, actually, I need to find out the ratio between delta x, delta y, and delta v, delta u, and delta v, just as we did in the single variable function case. So first of all, each point x star and y star in the domain D is mapped uniquely from E by T. So since T is a bijective map from E to D. Okay? And second, the area so although in this case we take the D as a rectangular cube, so delta x delta y doesn't change at the point x star and y star. So whichever point I choose in the domain D, delta x delta y, assuming that I take the subdivision as an equal subdivisions, it's always the constant. But if my domain D is not a rectangular cube, then if I take the delta x delta y, or if I take the non-equal distance, equally spaced subdivisions, then delta x delta y would be different. However, the area delta x delta y should be expressed in terms of delta u and delta v, or delta u delta v, with that's the important part, with a factor. So there should be a modifying factor to identify delta x delta y and delta u delta v, and that factor is called, let's say, j uv, so that I want to replace my delta x delta y as almost equals to j times uv times delta u delta v. So this juv is a function of u and v. So what I mean by that is the ratio between delta u delta v and delta x delta y depends on the point where you're looking at. So if you're looking at this point, then if I increment my u in this amount and v in this amount, then there will be a corresponding increment of delta x and delta y. Right? It should not be like this horizontal or vertical increment, but anyway, there's a area, corresponding area. But if I take another point inside of E and take the same increment of u and same increment of v, although uv doesn't change, delta u delta v remains the same, because of the function, the nature of the function, the x and y at the different point might increase in a different ratio than delta x delta y in a different point. Okay? So there should be a function, it's not always 1, to identify the ratio between these two areas. All right. So problem is, question, I can identify delta x star and y star using this map T, assuming that map T is fully known. The question is how to find this factor. How to find this factor. Maybe I should erase this and then write it later. So let's think about the transformation. Let's focus on the transformation. So it's a map from uv to xy. Okay. Let's say I pick a point in uv as u0, v0, okay? Or let's say here is u0, here is v0. And I want to increase my u, so that by taking v fixed. So I'm moving horizontal direction. So I'm going to take this as a C1t, okay? And I'm going to define another path that fixes u and then increase v. So that's called C2t. All right? So if I take the t, if I take the image of t along this curve C1 and C2, when t equals to 0, I'm assuming that it starts from u0 and v0. Okay? C0 equals to C20. So it should start from some point in xy plane, let's say x0 and y0, assuming that t maps u0, v0 to x0, y0. And let's say I'm following a C1 path. Then it should start from x0, y0 and move along some curve. Okay? Although I'm moving straight line, the image should not be, maybe in general, should not be a straight line, right? It can be any curve. So I'm taking some curve here. And also, if I move along C2 curve, then it should move along some curve inside the xy plane. So I'm going to take this as D1, meaning that this is the composite of C1 and T, and this is D2, and this is the composite of C2 and T. Okay, so how do you measure area bounded by two vectors? So which means that I want to find out the small area with a small increment of delta u and small increment of delta v. Okay? Let's say I have a same time frame for UV plane and XY plane. Let's say my delta U is displacement of the point along C1t curve during the delta t amount of time. Okay? So if t is the time is past delta t amount, then delta u is where I landed after I followed the C1t curve. So that means I'm taking C1 prime 0, which is the initial velocity along the C1t, and then delta t. Of course, if my C1t is not moving in a constant velocity, then this is not equal, but it's almost equal. Right? If delta t is getting smaller and smaller, so that's the delta u. And what's delta v? So since I'm moving vertically, so if delta t amount of time is passed, then delta v is approximately the velocity, or let me make a absolute value sign here, because this is the vector, so I want to take the speed, right? So I'm taking the vector here. And then delta t, okay? That's delta u and delta v, okay? So I said that I'm assuming UV plane and XY plane has the same time frame. So if I move my point along C1 and C2 in the same time frame, then there should be a same movement and the same time frame in XY plane. So it moves along D1 and D2. Okay? So let's say I have moved, yes?
Why you choose the C2 prime T?
0. Yeah, thank you. So once you start moving from UV, then in the range space, it moves from x, y, and the velocity along d1 is d1 prime 0, and we have d2 prime 0 when you move along c2, right? If you take the delta t amount of time, it will only move, so this is the speed of initial velocity, okay? So the actual distance you moved is taking the multiplication of speed times the time, amount of time. So actual movement is something like this amount. This is d1 prime 0 times delta t, and also this amount, which is d2 prime 0 delta t. Okay? So I want to compare the area of this rectangular box with area of parallelogram bounded by these two vectors. So I'm taking this as the size, but the vector is d1 prime 0 times delta t. Okay. So let's take the area here. So I introduced the notation, but you have an easy way to compute this rectangular box. So how you compute the rectangular box is just first you take the vector of this length, which is c1 prime 0 delta t, and then this length, which is c2 prime 0 delta t. And okay, so let's leave it here. And then also let's talk about how to find the area of parallelogram bounded by these two vectors. So this vector is d1 prime 0 delta t. So d1 prime 0 could be long vectors, but we're not moving in one unit of time. I'm moving only by delta t unit of time. So it should be a very short vector. And then this is also d2 prime 0 delta t. How do you find area bounded by these two vectors? Area of a parallelogram. Cross product, right? So although this is a two-dimensional vectors, you can take the cross product. The one way you can do that is, I have to introduce some notations here. Let me write it here. So it's going to be a little long computation. So let's say C1t is it's fixed on v coordinates. So x1t, u1t, v0, and c2t is u0, v2t. Then also let's say t is function of uv. So coordinate for xy is a two-variable function on uv. Okay. First of all, let's try to compute the rectangular area using the cross product. If you forgot about what's cross product and why cross product gives the area of parallelogram, let's say I have two vectors on xy plane, let's say u and v, and the cross product of this uv in a three-dimensional space gives a vector which is perpendicular to both u and v, which means that it should be a vector parallel to z-axis, right? But the size of this cross product, u cross v, is the area of parallelogram bounded by u and v. Okay? So u cross v is a three-dimensional vector whose size is this area. Parallelogram bounded by u and v. So I'm going to use this. I don't care about three-dimensional vectors. I only care about this area parallelogram. But this C1, C2 are two-dimensional vectors. But I can think that as a two-dimensional vector in xy plane having 0 on the z coordinate. So I'm going to replace this C1, C2 by three-dimensional vector whose third coordinates are 0. So let's say this is du dv, meaning that it's the area of this small part, and this is dx dy, which means that it's the area, corresponding area of these small parts. So du dv is equals to cross product of u1t v0 0 cross product and u0 v2t. Sorry, so I should take a prime here, right? So let me write it again. So we have C1 prime 0 is U1 prime 0, 0, and C2 prime 0 is equals to 0, V2 prime 0, and 0. What we have to take the cross product is these two vectors, right? C1 prime 0 delta t and C2 prime 0 delta t to get the area of parallelogram. So the area du dv is equals to the absolute value, the size of vectors of u1 prime 0, 0, 0 delta t. That's the vector, three-dimensional vector, okay, from C1 prime 0, okay, and then cross product of 0, V2 prime 0, 0 delta t. Sorry, is that delta? Is that delta t? Yes, delta t, right? Let's take the cross product of two three-dimensional vectors. So we have 2 delta t, so we can take that out. And if you take the cross product, did I mention how you take the cross product, right? ijk, or e1, e2, ek, e3, and then u1 prime 0, 0, 0, 0, v2 prime 0, 0. Okay? So when you do that, there are lots of 0. You take the determinant of this 3 by 3 matrix, then what only survives is these parts. Everything else has 0, so it kills. And you take the absolute value of that. So basically you have a three-dimensional vector whose third coordinates are non-zero, and that value is u1 prime and v2 prime. And you take the size of that vector, which means that you only take the size of the third coordinates. So that's u1 prime 0, v2 prime 0, delta t squared. So assuming the delta t is always positive, this is our area, the du dv. Now, let's take the area of dx dy. So dx dy is not rectangular area. It's an area corresponds approximately corresponds to the rectangular area in UV plane. So dx dy is, again, it's can be computed by the cross product of what? So first of all, you take the d1 prime t, right? Let's take the d1 prime t here, d1 prime 0, and because we are taking t equals to 1, t equals to 0. So that's the derivative of the composite of two functions, right? So this is dt times c1 prime 0. So dt is computed at t equals to 0. So I'm going to write, for now, this is, although this is not a standard notion because we agree that we are going to compute the differential of t when time equals to 0. That's what I'm saying here. So let's quickly compute that. So t is a function of x and u and v, and has a x, y here. So what's the differential? It's a 2 by 2 matrix, right? First row, first column is, right, xu, xv, yu, yv. And we are compute these partial derivatives at t equals to 0, which means that when t equals to 0, uv are u0 and v0. So I'm taking these coordinates applied here. And then what's c1 prime 0? So I put that here. So it's a 2 by 1 matrix, right? First row is, right, u1 prime 0, and second one is 0. So let's write here. So what's the first coordinates? Of d1 prime? How do you compute the first coordinate of d1 prime? Multiply xu with u1 prime. So I'm going to drop u0, v0, and well, let me write it out here. So for okay, so although it's going to be the long formula. So this is the first coordinate, and what is the second coordinate? This one, right? So we have yu, u0, v0 times u1 prime 0. So that's the two coordinates for d1 prime. But in order to find the cross product, we have to make it into three-dimensional vectors, as if it's lying on the xy plane. So we have we add one more coordinate, 0, in the third coordinate. And then that's not it, because we are going to take a cross product of these vectors, right? We had delta t multiplied, so we have delta t. And then cross product with, now d2 prime. So we compute this d1 prime using the chain rule, but also there are lots of forms of chain rule. So if you think about the composition here, so t has a formula there, so and C2 has formula here. So this is basically you plug U0 on U and V2T on V. So basically this is X U0 V2T, Y U0 V2T, right? So if you plug in here, then, so these, if you think about the D2T in the final form, it has two coordinates, and every coordinate is a function of t. There are only one variables. So when you take the derivative of t, you're taking a derivative of these two single variable functions. Right? So if you take the single variable function, which is a composite of multivariable function, you can apply your chain rule in a different format, which is, so d2 prime 0 is first you take the ddt of t equals to 0 of x u0 v2t, right? And then take the ddt of a t of u0 v2t, right? Let me write it here. So what happens? So x is two variable function, and inside you have one variable function. The chain rule says that if you want to take this kind of composite differential of composite functions, then you first take the partial derivative of x u, and then you take the derivative of u part. ddt of u0, but u0 is a constant function, so if you take the derivative, it goes to 0, so it disappears. And then you add with partial derivative of second variable, and then multiply it with the derivative of second variable function at 0. So that's the first coordinate, and second coordinate is similar. I'm sorry, so yeah. So same thing right here. We have y here. So if you take the partial derivative of y by u, then you have to multiply that with derivative of u0, which is a constant function, so it goes to 0. So you only have yv, and then multiply with v2 prime 0, right? So summarize, you have xv times v2 prime 0 and yv times v prime 0 as a d2 prime. So that's what should go here. So xv u0 v0, v2 prime, and yv u0 v0 v2 prime. And I have to make it into three-dimensional vectors, so I add one more component, 0, and then multiply by delta t. So that's the three-dimensional vectors that I want to find out the parallelogram area of a parallelogram bounded by that vectors. Let's make it a little bit more easier. So because we have a value multiplied on each of three components of first vectors, right? 0 is 0 when I multiply u1 prime. So you can always assume that this u1 prime is multiplied on these three coordinates. So I can take out this u1 prime outside, and then our vector is of this form. And also I can make into simpler form, yv u0 v0, comma 0 times v2 prime 0. Okay? Again, these are just values, real values. And after I've done all the computation, I'm going to take the absolute value of the vectors. So that means it doesn't matter how long it doesn't matter about the sign of this real value. It only matters about the size of these real values. So I can take out these terms outside of this absolute value sign. Basically, this is xu, yu, 0 cross xv, yv, 0. And then this is u prime 0, v2 prime 0, and then delta t squared. All right, let's compute this. So if you compute that, it's ijk of xu, yu, 0, xv, yv, 0. And then you take the absolute value, the norm of this vector, the size of vectors, and then you multiply that. So what's this? What's this part? So if you try to compute anything contains I, then you always encounter 0. So that disappears. If you try to get something including j, then also encounter 0. So this is removed, and you only have k parts, which is the third coordinate survives. So you take plus of these and minus of these. So basically you get x, u, y, v minus x, v, y, u as a third coordinate, and first and second coordinates are 0. If you take the norm of that vector, then you basically take the absolute value sign of that third coordinate component. So that's it. And then multiply with u1 prime 0, v2 prime 0, delta t. So that's that dx dy. Let's compare that with du dv. So that's our du dv. And this is our dx dy. So we have a common factor, right? u1 prime, v2 prime, and delta t squared are common. So dx dy divided by du dv. So I'm not saying symbolically you can take the ratio between these dx and du or dy dv. I'm taking this whole thing, dx dy and du dv, as one symbols, okay? So don't make a mistake whenever I says that this is one symbol. Okay? I'm not taking dx dy as a dx times dy or have any other mean that just the area of this just parallelogram. So that's equal to what? This one. They only have surviving factor is this thing. So you have x, u, y, v minus x, v, y, u. And this is not a formula. This is the value computed at u0, v0, because that's how we did it. And I just omitted here for simplicity. So you have to compute that at u0, v0. Okay? Okay, so let's summarize the substitution here. First of all, I wanted to compute a double integral of two-variable function defined on xy plane. But somehow it was hard, so I want to change it to the variable, change it to uv plane. Okay? So then everything I can compute on D is one-to-one mapped to a point in E, so I can simply change my domain of integration from D to E. But then I have to map a point in D from point on E. So I have to take a composition of F and T, because T is the map which connects the point from E to D. Okay? And then I have to also change my dx dy, which represent the small area on xy plane, to small area on uv plane. But as we observed in this long computation, the ratio between the area corresponding from uv plane to xy plane has the ratio, this ratio. So you have to compute. So this is the value of function. You have to multiply this amount to the value of function to make it equal, because this thing works as the ratio of dx dy. So in order to have dx dy, you have this ratio constant times du dv. Okay? That's the integration by substitution. So look at this left-hand side. This is the integration in terms of xy. You should do on xy coordinates, whether you want to use the Fubini theorem or not. Everything is in terms of xy. But what I'm trying to explain with these all explanation is why this equality happens with this integration. So first of all, look at this right-hand side integration is all in terms of uv. So x, u, y, v, x, v, y, u, these are the function of uv functions. Okay? So x, y are just the name of that uv function, which is the first and second coordinate function of t, the transformation function t. And then if you replace your if you take the composition of f and t, what happens is first you have fxy function, but you replace x with xuv and y with yuv when you do the composition, right? So this is f composite t. So now it becomes a function of uv. So everything is in uv. Even E is a domain in uv plane. Okay? So we have substituted xy using uv. So this factor is the most important thing, because it simply says that you cannot just replace xy using the transformation. You have to multiply some modifying factor to make it equal. So this is called a Jacobian. And this is called J in general, JUV. That's our J we posed in the first time. What's J? This is our J. Let's see some examples. 네. 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 So this is basically J U0 V0. Okay. So why did I take U0 V0? Because I'm taking dx dy dv du dv as at the point U0 V0. I can change my U0 V0 to any place, any point in the domain E. So basically, it's a function of UV. So that's how I get here. Jacobian is not a constant function. Jacobian is a function, but it's not constant. Let me give an example. Good question. So let's think about polar coordinates. So T maps r theta to xy, which is r cosine theta, r sine theta. So you can imagine that this is r cosine theta is xr theta, and r sine theta is yr theta. So let's try to find out the area of unit disk. So this is x and this is y, and we have radius 1. And how would you express the area of a unit disk in terms of integration of x and y? So let's say this is our unit disk, and if you simply want to find the area, you can take a constant function 1, right? And then integrate over d. That means you get a volume of a cylinder whose base is a unit disk with a height 1. So the volume is same as the area of the disk, right? And we know that the answer, which should be pi, that should be pi. But without that knowledge, how would you compute this? So there are ways to compute this. There are easy ways to compute it using Fubini's theorem, but let's use the integration by substitution. Okay. So I want to change my domain of integration d to e. And luckily, since we have 1, which is a constant function, even if I take the composition with this transformation, it will be a 1, right? It's always same as 1, so I don't have anything changed here. But I have to change my dx dy in terms of dr d theta, because that's the coordinates that I want to map to xy plane. Okay? So let's look at what t looks like. So t is r theta to xy plane. Okay, so if you want to map the unit disk on xy plane, how far your r should go from 0? 1. How far should theta go from 0? 2 pi. And if you want to make it into one-to-one function, what kind of boundary that you have to include or exclude? 0, yeah, you can exclude 0, or include 0 and exclude 2 pi. But let's say this one. So you might include one of the left-hand side, one of the horizontal boundary and one of the vertical boundary. So this should be almost one-to-one, but there's one point that actually cannot be one-to-one at all. What point is that? What? Sorry? Origin, yeah. So if you omit the origin, then there's no way you can map the origin on xy plane. But if you include the origin, then all the points on this line is mapped to the origin. So it's not a one-to-one map, right? But if you try to exclude all of these points, yeah, if you include, so maybe if you want to really accurate about this, then maybe you can exclude all of this thing and only include this part, right? Mm-hmm. Yes?
Why you exclude r equal 1?
Why do I exclude r equals 1? Right, I don't have to exclude r equals 1, right? In order to have a boundary. Okay. How about theta? So if I keep theta to 0, then I basically have this line, but that's okay. So, okay, so maybe, yeah, maybe this is the one-to-one map. So if you take any point in here, then it will get the one-to-one. But later I will say that this, you don't really have to exclude the boundary. Okay. But for now, let's make it into one-to-one function. So what's the thing that should go here? First of all, xy is xy, uv is changed to r theta. So this is equals to x r y theta minus x theta r y. Sorry, y r d r d theta. And what's E? E is this guy, right? Let's put it here. And what's XR? What do you get after taking cosine theta? Yes. And then Y theta? R cosine theta. And X theta? Right, so you have minus, so you get plus R sine theta. And XR, YR? Y is this guy. Yeah, just the sine theta, right? All right, so we have dr d theta. And we have r cosine square plus r sine square. So it's simply r. And inside of this domain E, r is always positive, so I don't have to put the absolute value sign. So basically, it's r dr d theta on this domain E. Now, if you think about the function r inside of r theta plane, is it a continuous function or not? It's a polynomial. It's always defined on the entire r theta plane, and polynomial is always continuous, right? So think about the theorem that if your function integrand is continuous function on a bounded domain, then you can use the Frobenius theorem. And if you integrate over a boundary, since boundary has no area, it really doesn't change your integration. So you don't have to worry about the domain have no boundary on this left and upper corner when you integrate the function r. So we can safely just use the Frobenius theorem as if your E has the boundary on the full sides. So basically, the computation goes with the Frobenius theorem, and so let's take a R domain first. So 0, 1, and theta is from 0 to pi, and r dr d theta. D theta dr for iterated integral, and so r is a constant when you do the integration by theta. So 2 pi r dr, and then now we have 2r, so we have pi r squared from 0, 1, so we get pi, right? So Bonje asked the question whether you have a constant Jacobian here. No, you have non-constant Jacobian. It's r. It changes. Depends on the point where we're looking at. So what is going on when you compare the area is that, let me enlarge the polar coordinate picture here. So if your r is small, let's say theta is right here. You're looking at this point. Let's say r is like 0.1 and theta is pi over 4. And you want to find out the small area by increment the r and theta here. Then the corresponding area to this transformation is you have r, which is distance from the origin, which equals to 1/10. And then you increment your r a small amount. So you're looking, maybe I can exaggerate here. So we have 1/10 of length from the origin, and then with the pi over 4 degree angle. And you have increment r by delta r here. And you also increment the theta by d theta. So if you increment your d theta, then it's like you're taking these ray increased by delta theta d theta. And then you're looking at this pi shape area, which corresponds to this area. Since T is a one-to-one map, every point in this rectangular box is mapped into this pi-shaped thing. Okay? Of course, you can find the exact area by using the formula, but that's pointless because we are going to take this dr and d theta goes almost equals to 0, and what we really need to know is the ratio between, approximate ratio between this area and this area. So if your R is large, for example, if you take like 9/10 of area with the same increment of R and theta, what happens? So you're far away, like here, right? And let's say this is like now 9th, 10, and then you have the same increment of theta, then you have a quite larger pi here. So in R theta plane, the area of rectangular box is the same, but corresponding area on xy plane is different. It totally depends on the where you compare the domain and the codomain. Then this Jacobian says that it only depends on R. Okay. Of course, you can have some situation like Jacobian is constant. So let's say another example. I want to compute sine x plus y dx dy on the domain D where let's say I want to make a parallelogram here. So maybe I made it wrong here. So this is the picture. So this is 1, 1, and this is minus 1. Okay, so this is our D. So maybe you can compute using the Fubini theorem, but there's a clever way to do that. So I don't want x plus y to just two variable inside of sine. I just want to make it into one variable. Let's say I want to make it into u. Okay. And let's look at the domain D. So it seems like D is expressed by two inequalities that x plus y is bigger than 0 but less than 1, and y is bigger than 0 and less than 1. So if your x comma y satisfies these two inequalities, then you always fall into this domain D. Now, if I replace x plus y with u, and then if I replace y by v, then I can make a transformation T which maps uv to xy, and then this transformation is mapping u comma v, which is in 0, 1, 0, 1, to this parallelogram. This is u and v. Okay. Now, it says that u is equals to x plus y, not x equals to u plus v. Okay, so I have to find the formula of x and y in terms of uv. So what's x? So I'm wanting, what is it? U minus v, yes. And then y is v. So that's our t. And then, so this integration now becomes the integration on, let's say, E, but it's simple. It's a unit rectangle, and of sine u. And then I have to multiply Jacobian. But let me introduce an easy form of memorizing the Jacobian. So Jacobian for two-dimensional transformation is the following. Definition. So we have transformation Rn to Rn. Jacobian of transformation T is equals to the determinant of differential of T. For example, if T is uv to xy, then jt is absolute value of determinant of xu, xv, yu, yv, and absolute value of the determinant. So basically it's xu, yv minus xv, yu. So that's the same formula we had before. So I'm going to write that out. So we have determinant of 1 minus 1, 0, 1. Okay? Of the UDV. So luckily we have a constant Jacobian, so we don't have to worry about the substitution. But now just 1, so it becomes 0, 1, 0, 1. My Fubini theorem is an iterated integral of 0, 1, 0, 1 sine u du dv. So if you take the sine integration, it's minus cosine u from 0, 1. And then if you integrate over v, then it's a constant, so nothing happens. So that's the result, 1 minus cosine 1. Okay. So if you want to find out the integration using Fubini on xy plane, you have to, let's say, take the iterated integral on these direction, then you have to find out the bounding functions of minimum and maximum value of x and so on. And you have x plus y inside of sine, so you have to worry about how to take the integration. But if you take the substitution, it gets easier. So I made up this example to make it works, but it's just a problem for problem. Let me make few remarks here. So usually we are given with a function that can be integrated with, which cannot be integrated directly. So we have to make a substitution, integration by substitution to make it into integrable form. So that involves like what kind of variable that I should replace with. So something like x plus y should be replaced with u in order to make it simpler. So I have a function of x and y in terms of function of u in terms of x and y, not function of x, function of u comma v, function of x and y in terms of u comma v. So if we find the formula for u and v in terms of x and y, that means I know what to substitute. Let's say I want to substitute some formula of x and y by u and some formula of x and y by v. Then this is not the coordinate function of transformation. This is the coordinate function of inverse of transformation. Then we are taking the inverse of x and y, and this u, xy, v, xy is the coordinate function of inverse of function, right? So we cannot take the Jacobian of this, right? We have to take the Jacobian of inverse function, right? Jacobian. So not the inverse of Jacobian, but the inverse of Jacobian, the original Jacobian, is given by the reciprocal of Jacobian of the inverse of the function. That's the first remark. So let's look at this one. For example, if we found a so u is x plus y and v is y, then P inverse maps xy to uv, and that's x plus y, right? So what's the Jacobian of inverse? So in this case, we are taking xy as an independent variable. So it's determinant of N101. And that's 1, right? Therefore, the reciprocal of 1 is 1. So that's actually equals to original Jacobian, Jt. So that's a kind of trivial example, but it works for any type of transformation. So for example, if you replace your complicated formula of x and y with some simple symbol like u or v, then don't try to find out the t. Just leave it as the inverse of t, and then try to compute Jacobian and then take the reciprocal. That's the Jacobian. We will have some equation. I mean, we will have the examples later, but not for now. And once we practice some examples, then you will know what I'm talking about. And also another remark is that this integration by substitution doesn't only work with two-variable function. You can apply to three-variable function. So let's say we have t, which is a transformation from R3 to R3. Sorry, so not entire R3. Let's say V to W. Okay. So we have triple integral of three-variable function on x, y, z plane. Okay. Let's say our t is sending u, v, w to x, y, z. Okay. So then I can make this integration to the integration of u with w. So I have to take the composition to make a function of u with w, and then I need du, dv, dw, which represent the small volume on this u with w plane. But I need a vector to retrieve the volume of corresponding area volume in xyz plane. So that's the Jacobian of t. Jacobian of t here. Maybe I can write here. So where Jacobian of t is equals to the f-loop value of dt, determinant of dt. So dt is a 3 by 3 matrix. You can find the determinant, and then you take the f-loop value. That's the Jacobian jt. Comes here. So I like to mention that Jacobian t, usually in the usual context, they don't put the f-loop value sign to define the Jacobian, which means that Jacobian could be negative. But and then, I mean, in the formula of integration by substitution, they put the f-loop value sign here instead of here. But I put the f-loop value sign here because we're not going to talk about orientation. So if you're trying to think about the orientation of a space in a higher dimension, then the sign of determinant matters, but we're not going to talk about that. Maybe at the end of the class. So that's the difference. And then we have a triple integral here. So let me give an example of that the last remark, that we can apply the integration by substitution for triple integral. Let's find the volume of a sphere. I mean volume of the ball. Let's say I'm going to talk about the spherical coordinate given by r theta phi. So remember that r theta phi is the following quantity, that if you have x, y, z, then you have a sphere of radius r, and if you take any point on the sphere of radius r, the distance from the origin is r, and you have angle from z-axis, which that's theta, and if you project your point on the xy plane, then the angle that this point connecting to the origin makes with the positive direction of x is phi. Okay? So you have x coordinate equal r sine theta and cosine phi, and r sine theta, sine phi, and r cosine theta. These are x, y, z coordinates in the spherical coordinates. We can take it as a transformation for a certain range of r and theta. So r should be from, let's say, if I want to compute the volume of a unit ball, r should be from 0 to 1, and theta from 0 to pi, and phi from 0 to 2 pi. Now, there's a question you can ask at this moment, because just as the case for the polar coordinates, if I include all the boundary, this map is not a one-to-one map. This is not a one-to-one correspondence. For example, if r is 0, then every point, if I choose any theta and phi, it maps to the origin in xyz plane. And also, if I take the theta, both 0 and pi, that's okay, but let's say if I take the phi from 0 to pi and include 0 and 2 pi, then it maps to the same point. So it's not a one-to-one map, but I'm going to throw these boundaries anyway, because if I want to integrate after changing all the variable to r theta phi, what I'm trying to do is, by including the boundary, I'm adding the boundary of this rectangular domain of r theta phi. And boundary doesn't have a volume. Okay? In the three-dimensional space, if you have a rectangular cube, if you take the one side, one face of the rectangular cube, that face doesn't have a volume. It's a volume 0. So it doesn't change your integration. So, so the volume of unit ball is equal to, let's say ball is ball here, integration of 1 on dx dy dz, okay? But that can be substituted by, so ball can be mapped by the rectangular cube of this range. Let's say this is V here. So V is in r theta phi plane. Integration of same 1, because this is constant, doesn't change the value. And now it becomes r theta phi, but we need a Jacobian to make it into xyz ratio. So let's compute the Jacobian. So I said that Jacobian is always given by the determinant, absolute value of determinant. I'd like to explain why. After we compute this, I'd like to mention why this determinant works as a Jacobian for three-dimensional case. But for now, just compute. So we have dt equals to 3 by 3 matrix. First coordinate r theta cosine. I take the partial derivative of r sine theta cosine phi. And theta, we get r cosine theta cosine phi. And phi minus r sine theta sine phi. And sine theta sine phi r cosine theta sine phi minus r plus r sine theta cosine phi, and cosine theta minus r sine theta 0. Right? This is the determinant. I mean, this is the differential, and then we take the determinant of this. So remember again that you're adding in these directions. Okay, so this becomes 0. So we have r square sine theta cosine theta cosine phi square. I'm taking these two with this cosine theta. And then I'm taking these two and that, and plus r square sine square theta, actually cube, right? Cube and sine square theta. Is that right? Right. And then we have a negative. So these negative becomes 0. So we have this negative and this negative. We have minus of minus, so it's a plus. So r square cosine square sine and sine square phi. And then here we have minus minus r square, so it's plus r square, and sine cube cosine square phi. So we have canceling out. So this one are not canceling. It's combined to sine square sine r square sine cube, and these two combines to this. So this is equals to r square sine theta cosine square plus r square sine cube. And what's this? R square sine theta, right? Because you have sine square, cosine square. So that's it. And then we have always absolute value, but look at the theta. We have only from 0 to pi. So sine is always positive, so I can omit this absolute value. And then let's compute. So by Fubini's theorem, I take 0, 1, 0, pi, 0, 2 pi of r squared sine theta. So dr, no, this one is d phi, d theta, and dr. And that's, so basically we don't have phi here. We can take out 2 pi. And then if you take the integration by theta, if you integrate sine over 0 to pi, it's 2, right? And then you integrate r squared from 0 to 1, what is it? 1 over 3. So 1 over 4 pi, which is the volume of a unit sphere. If you replace, let's say, radius by r, then you get r cubed, right? You get the general formula for the volume of a sphere, volume of a ball. So you don't have to slice your 3D object to find the volume anymore. You can just parameterize your volume in a nice way so that you can just simply take the triple or double integral to find the volume. Slice is, I mean, that's funny things. Why do you have to slice it? Why do you have to rotate to find the volume? Right? It's nonsense. So let's try. Let me explain why the determinant gives the Jacobian. So the meaning of Jacobian is you want to find the ratio between the original volume and the corresponding volume. So here is UVW plane space, and you have a transformation which maps to XYZ plane. Now I want to take a point in UVW plane and then try to look at some cube. So that cube has width, length, height. Okay? So let's try to think about the vector that's starting from the point, the original point. So this is U0, V0, W0. So let's say the corresponding point is X0, Y0, Z0. Let's say I'm moving along the y direction, fixing with V and W, and also moving V direction and W direction. So this delta V, delta U, delta W is the displacement of this movement after a small amount of time t, right? And for simplicity, let's say I'm moving in a unit speed, okay? So basically, I can say that this delta V, delta U is delta W are the amount of time that I moved along that coordinate direction, okay? So suppose that I have 3 different time amount or timeline that I can move along each coordinate direction, okay? And let's imagine what happens on the ranged space. So it's always start from this point. Let's say I give a name for this, C1, C2, C3. If I move along C1 curve, then I would move along some curve inside of three-dimensional space, and C2 curve and C3 curve. Let's say I make another vector here. So let's say I'm moving in this direction at the time t equals 0, and this direction and that direction for each C1, C2, C3 direction. Of course, this is approximate direction. If I take the longer time, then I'm not moving in this direction, but if I make it this delta V, delta U, delta W smaller and smaller, then this curve will almost equal to this straight line direction. Now, the problem is this has a curve. So this curve is given by, if I'm moving only the U direction, so U direction, so it's T V0 W0, and this curve is when I move along C2 curve, so this is U0 T W0, and this is U0 V0 T, right? Okay, so let's think about this vector. So what is this vector? I'm taking a derivative of t of this vector, this coordinate function. I mean the parameterized curve, right? So this is t prime 0. Yeah. So I'm taking a derivative of these functions. So maybe I should, for simplicity, just take it as d1. Okay. So d2 and d3. So let's compute d1 here. This is the vector when I take the derivative of t of this parameterized curve. But this parameterized curve has coordinates. So it's xt, v0, w0, yt, v0, w0, and zt, v0, w0. Although this is just one parameter curve, it's parameterized by only one variable t. Each has 3 coordinates. I have to take a derivative of each coordinate functions. So when I take the derivative of this function, it's a composite of 2 functions. One is the 3-variable function x, and the other is a parameterized curve in UVW plane. So when I do that, this is xu times t derivative, which is 1, and xv times v0 derivative. But what is v0 derivative? v0 is constant. So when you take the derivative in terms of t, it's 0. So it disappears. It's also same for w0. So you only have xu, and that's when t equals to 0. I'm sorry. I made a big mistake here. So u0 plus t, right? v0 plus t. w0 plus t, okay? u0 plus t. Sorry. u0 plus t, u0 plus t. So when t equals to 0, we are looking at u0, v0, w0 space of the partial derivative. And here, same thing. This is yu, u0, v0, w0, and zu, u0, v0, and w0. Basically, the vector d1 is xu, yu, zu. Okay? This is xu, yu, zu. And what is d2 then? I'm moving v direction for d2 and see how the corresponding curve in a range space looks like. Right? I'm just moving v. That means I'm making a partial derivative of v. I'm looking at the rate of change in terms of v. So this is xv, yv, zv. And what is d3? xw, yw, and zw. And then this is the speed, but how far I actually go when I change my time from delta u, delta v, delta w is multiplying this amount, this v, and this amount, the size of each vector with a multiple of delta u, delta v, delta w is actual distance I move from the origin to the point, to the end of this rectangle. So if I want to find out the ratio between the rectangular cube in UVW plane and corresponding volume in the XYZ plane, then I have to find the volume of parallel pipe thing in XYZ plane. Of course, it's not an accurate volume, but it will be fairly accurate if I take the delta U, delta V, delta W really close to 0. So I don't have to worry about having an error. So how do you get the volume of parallel pipe? Parallel piped region here. How do you take the volume of parallel pipe region bounded by 3 vectors? So let's think about the picture here. So we have, let's say our 3 vector is UVW for ABC, for example. Let's see here. So parallel pipe has a parallelogram shaped bottom here. And then what you have to do is find out the height of this parallel pipe and compute that, right? So the area here is same as A cross B, absolute LU, right? So area is norm of the vector A cross B. And what's the height? If you know the theta between, so if you know the theta between the orthogonal vector to A and B with C, so let's say this is theta, then the height is C times what? Cosine theta. So basically the volume of this parallel pipe is bounded by ABC is A cross B times C times cosine theta, where theta is the angle between. So I made a picture like this one, but what kind of vector is this? This vector should be the vector parallel to perpendicular to A and B at the same time. So that's the A cross B, right? So I can say the theta is angle between C and A cross B. Okay, so this looks familiar. So if you have a norm of 2 vectors multiply with the cosine of angle between these 2 vectors, then it's an inner product. A, B, C. Okay, so what's the relation between the Jacobian with these observations? Jacobian is that A cross B inner product C. So let's look at the Jacobian. So first of all, I can say that this is equals to C times A cross B. right? So inner product can change the order. So let's say, so I made a D1, D2, D3. I want to take D3 times A1 cross D1, D2. So then I get the volume of parallel pipe. So D3 is D3, but D1, D2 cross product can be given by ijk of D1, which is xu, yu, and zu, and xv, yv, zv, okay? And then this thing is nothing but a vector, although I made a notation like determinant, but it really means it is the I is a symbolical 1, 0, 0 vector with multiplied, the constant multiplied, and j and k are also vectors. So this is a vector, three-dimensional vectors. When you multiply, when you take an inner product with two three-dimensional vectors, for example, if you want to take an inner product with xw, yw, zw, and some vectors. I don't care about the sign here, so some sign, some constant should be appear here times I. Something appears here and something appears here, right? What I'm doing here is to inner product is just replace this xw with I. Then I get the multiple of this constant times this. And that's how you get the inner product. And also you replace that here, and you replace that here. Okay? So that's same as you take these three components on the first row of this 3 by 3 matrix. So this is equals to xw, yw, zw, xu, yu, zu, xv, yv, zv. Determinant of these 3 by 3 matrix. This is not quite a differential of the transformation because the order of rows are interchanged. But there is a theorem in linear algebra that if you want, if you have the square matrix and you want to find a determinant, the value of determinant doesn't change when you interchange two rows. So this is equals to interchanging these two rows. xu comes first, and rest of us. And then you can interchange the second and third row to get xu, xv, xw, and so on.
So maybe we can just change the initial setup. Like we can, the D1 and D2 can move parallel to the left side, and send the D3 to the right side of the. I mean, like the equation. Actually, we're calculating the volume, so the D1 dot product, D2 cross D3 is also equivalent to that equation.
Oh yeah, you can do that too. Yeah, so you can say that this is A and this is BC. Can be much nicer than these combinations. Yeah, that's good. Thank you for the suggestions.
One question. Is there any? I didn't follow why you multiplied the small change of
This one? Right. So this is a speed. This is a speed, and speed means that it's approximate distance when you move when the time is passed by 1. Okay, but I'm taking a small amount of increment, and I'm taking this C1, C2, C3 are unit vectors, so this increment is same as the increment of time. So I'm assuming that for u direction, I'm taking delta U time passed after I started at the origin here, U0, V0, W0. So I have to multiply that time amount, delta U, to approximately find out where I landed after that delta U time passed.
You mean the delta U is equal to the t?
Yeah, so in some sense, it has the same role of delta t. So in the previous observation, we had a delta t here, but I'm taking that delta U is same as delta t. Okay. Just for simplicity, okay? Because I don't want to make a general argument about the movement in the UV plane. I'm taking all the movement to be a unit speed unit movement. Yes?
What's the full word of the abbreviation of PP?
Parallel pipe. I'm not really sure I spelled correctly. Parallel pipe. Parallel pipe. Is that correct? Okay.
You mean in Korean 평행이면체?
네, 평행육면체요. Okay, so that's the. I think this is the most essence of the integration part. So once you understand the integration by substitution, the rest of the part, which is the surface integral and line integral and the integration by integration of vector field, it's just a combination of how we define the double integral and how we define the substitution. So let's call it here, and then if you have any question, please ask online or email. So from next time, we're going to discuss about the line integral, so, and also integration of vector field. And yeah, that's our plan. So thank you for listening and have a nice weekend. See you on next Tuesday.